So far, we've described the steps that produce the planets and many of their moons. But if we stopped here, we'd still have a solar system that would look very unfamiliar to us, and might even be uninhabitable. That's because of all the stuff that hasn't gone into making planets yet. The dust, gas, and planetesimals that did not eventually turn into planets. This includes most of the gas that was in the disk, and an unknown but probably large fraction of the planetesimals. There are probably even some planet-sized bodies that formed but which aren't around today. It's fairly easy to tell what probably happened to the planetesimals and protoplanets. Once Jupiter formed, it turned into the great broom of the solar system. Any smaller body that gets too close to it stands a good chance of being swept out of the solar system by its gravity.
When a giant planet scatters planetesimals, it sends them in random directions. So some of them will hit other planets or smaller bodies. This, along with the late stages of solid body accretion, helped cause impact cratering on all of the solid planetary surfaces in the solar system. It's likely that much of the water, carbon, and other light materials that we see on terrestrial planets came from outer solar system planetesimals that were scattered inward this way. Since living organisms on Earth are made of these materials, we owe our existence here to this scattering process.
Of course, not everything was scattered away. There are a few places in the solar system where planetesimals could remain without getting too close to any of the planets. That's where we now see the asteroid belt, the Kuiper belt, and the Oort cloud. These are all made of leftover planetesimals. Let's look more closely at some of these leftover planetesimals, starting with the asteroid belt. The asteroids probably formed in roughly the same part of the solar system we see most of them today, between the orbits of Mars and Jupiter. This straddles the boundary between the inner and outer solar system, and the composition of the asteroids reflects this. While some asteroids are mostly rock and metal, like the inner planets, others have a lot of ices and carbon-based organic material. There are even salts in some asteroids, like these white patches on the largest asteroid, Ceres. Jupiter is big enough that its gravity probably stirred up the orbital motions of asteroids. It's even possible that other protoplanets formed in this part of the solar system and later were scattered away to interstellar space by Jupiter. This stirring meant that the small amount of material that was left behind had little chance to accrete. When these bodies collide, they're more likely to shatter. We see evidence of this in the form of iron-nickel meteorites that have landed on the Earth. These meteorites appear to have formed in the deep interiors of large asteroids. These asteroids had to have been broken up by collisions to let their core material reach us here on Earth. The Kuiper belt is the set of small bodies orbiting just beyond the orbits of Uranus and Neptune. Like the asteroid belt, these may have also formed close to where they are now, meaning that they formed from a mixture of rock, metals, and hydrogen compounds in the form of ices and organic materials. There is some evidence that both the Kuiper belt and the outermost planets started a little closer to the Sun than they are today. The outer planets could have migrated outward through a mechanism we'll discuss in a couple of slides. As this happened, they forced the Kuiper belt objects to move away from the Sun as well. This process also stirred up the orbits of the Kuiper belt and prevented further accretion. This left a number of failed protoplanets. These bodies never got big enough to be considered planets today, leaving us with several dwarf planets in the Kuiper belt, including Pluto. The Oort cloud is also formed of ice-rich planetesimals, in this case in a spherical shell around the Sun, ranging from 1,000 to several tens of thousands of astronomical units away, meaning they're a significant fraction of the distance to the next star. Unlike the asteroid and Kuiper belts, the Oort cloud probably didn't form near where it is now. Instead, these bodies are likely to have formed in the outer solar system near the planets Jupiter and Saturn. When these largest planets formed, their gravity was able to scatter planetesimals right away from the Sun. While some of these simply left the solar system entirely, others didn't quite escape, and instead they got stuck in this very distant region where they can barely feel the sun's gravity. In fact, the sun's gravity is so weak at this distance that the orbits in the Oort cloud have been randomized over billions of years by passing stars and even the tidal pull of our Milky Way galaxy. The Oort cloud and the Kuiper belt are both far from the inner solar system, but they can still affect us. As we saw earlier, occasionally one of these objects is scattered into the inner solar system, where the sun's heat turns it into a comet. Scientists are very interested in studying comets today because they are the leftover building material for the outer planets. Removing the gas is more of a challenge. Some of this gas may have spiraled into the central sun, but that doesn't work for gas in the outer solar system. Jupiter gets in the way here. It's also possible that the sun's magnetic field played a role in accelerating gas out of the system. Jets like the ones in this painting are found around many young stars, and these appear to be generated by the star's magnetic field. Once again, this works best for gas in the inner solar system, but not so much in the outer solar system. A third option is that the sun's own high-energy photons knock gas out of the system one atom at a time. Young stars typically produce a lot of X-rays and ultraviolet light, and when these photons hit gas atoms, they give them enough kinetic energy to escape into interstellar space. This is one mechanism that works best in the outer solar system because the escape speed from the star is lower there. It's likely that all three of these mechanisms were at work in the early solar system, though we don't know how much of a role each one played. When I first started studying solar system formation in the late 1980s, there were a couple people who kept pointing out that there was one important problem that existed. Giant planets should move closer to or further from the sun after they form because of interactions with the disk and the planetesimals. At the time, most people didn't worry much about this, since the giant planets in our solar system seemed likely to have formed near where they were today, so this process couldn't be very important. However, in the mid-1990s, the first planets around other stars were found, and of course, many of them turned out to be giant planets in the wrong place, very close to their stars. In fact, they're much too close to form there. This generated renewed interest in mechanisms of giant planet migration. There are two main ways that a giant planet can move around after it forms. The first of these involves the cleanup mechanism we've already described. Whenever a planetesimal encounters a giant planet, it gets thrown either into the inner solar system or outward towards the outer solar system, or even right out of the solar system entirely. However, if we think back to what we learned about energy and orbits, if the planetesimal's orbit changes, the planet's orbit changes as well, in the opposite direction. Of course, the planet's orbit doesn't change much because the planet is much bigger. However, there were a lot of planetesimals to throw around, so eventually they could add up to more mass than the planet itself. If there's an imbalance between planetesimals tossed in versus tossed out, then that will make the planet migrate. Depending on the sizes and order of the giant planets, they can migrate either inward or outward. Models of our solar system suggest that Jupiter would be most likely to migrate inward because it tends to throw planetesimals right out of the solar system, while the other giant planets migrate outward because they tend to throw planetesimals in towards Jupiter. The other way a giant planet can migrate is through interaction with the star's gas disk. Remember that once a giant planet forms, it clears a gap in the disk. But the gas in the disk will still have a tendency to travel inwards due to friction. The fact that the planet has cleared a gap in the disk just means that the planet will be pushed inward along with the gas. The planet's own gravity ties it to the disk, so it spirals inward towards the star. This may explain why many solar systems have hot Jupiters. These are giant planets that have migrated extremely close to their stars. Of course, a migrating giant planet will stir up all of the smaller material it goes past, greatly complicating the picture of how planets form throughout the inner solar system. However, this raises another big question. Why didn't this happen to Jupiter? Recent work has suggested that the likelihood of this kind of migration depends on the balance between the rate at which gas spirals inward and the rate at which it is removed due to mechanisms like evaporation from high-energy photons. If this is true, we would expect to see a distribution of systems, some with giant planets that have migrated a lot and some that haven't moved far at all. Of course, this is a very active field of research at the moment, so our understanding of giant planet migration could change a lot over the next few years.
Here's another making sense exercise, but it's formatted a little differently from the others. Instead of a simple table, we'd like you to fill in this flowchart with the steps that go into making planets. Each box is an object we see in the forming or current solar system, while the links between them are the processes that get you from one to the next. Notice that the cooler parts of the solar system are at the top, while the warmer parts are at the bottom. You've got a list of what goes into all the boxes, so mainly you just have to fill in what goes where.
Let's summarize the main steps in the formation of a solar system. It starts with a cloud of gas of mostly hydrogen and helium, with just a couple of % of heavy elements. This cloud collapses under gravity to produce a hot central star with a disk of gas and dust around it. In the inner part of the disk, it's too warm for ices, so the only things that can stay solid are rock and metal. In the outer solar system, it's cooler, so there can be ices there as well. Also remember that most of the hydrogen and helium remains a gas in both the inner and outer solar system. In the inner solar system, the small amount of rock and metal around leads to small rock and metal terrestrial planets. In the outer solar system, the extra ices add to the rock and metal to make big protoplanets. These big cores can accrete lots of hydrogen and helium to form Jovian planets. In some cases, the giant planets can migrate into the inner solar system as part of the final cleanup phase, though that doesn't appear to have happened in our solar system. The outlines of this model of solar system formation were put together in the 1960s, during a time when there were few detailed observations of star-forming regions. Since that time, technology has allowed us to see evidence for all of the major steps in solar system formation. I'd like to look at some of this observational evidence here. The collapse phase is the best observed part of solar system formation. We've seen contracting protostars with disks around them. Here are some examples in Orion. It now appears that most very young stars have these disks. When we observe these disks in detail, we find the spectral signatures of fine grains of rock and ice, showing that condensation has been occurring. In fact, in this image, we can see two spectra of the same disk, the latter one showing that in just a few years, ice grains started to condense in the system. The most direct evidence for accretion comes from older disks around stars. These seem to be mostly dust, with very little gas. The one we're looking at is Beta Pictoris, an old edge-on disk. We saw this one in the last chapter, because this is one of the few systems with an extrasolar planet that has been directly observed. The fine dust grains that make up this disk can't stay in orbit for the 100 million years that the star has been around. Instead, there has to be a more recent source for this dust, and the best candidate is the sort of large collisions that we looked at in the late stages of accretion. The fact that we know there's at least one large planet in this system helps strengthen this conclusion. The effects of gas accretion can be seen in the fact that some of the disks we observe around newly formed stars have gaps in them, suggesting that there's a giant planet that has cleared a region around itself. Finally, the cleanup phase can be seen in the strong jets and winds coming from very young stars. In this picture, there's a protostar embedded inside the tip of this dense cloud. The two jets emerging from it are common features of newborn stars.